And for our final example, we have a little more complicated r value, but that's okay because that doesn't matter to us. We just simply need this to find the f prime of theta. So we get derivative of the first term times the second term plus derivative of the second term, cosine, times the first term. So this equals e of theta times cosine of theta plus sine of theta. And we know our x equals f of theta cosine of theta, and y equals f of theta sine of theta. So let's go ahead and apply our formulas. dy dx will equal dy d theta, derivative of the first term, e to the theta sine of theta, plus, or let's use our simplified expression, e to the theta cosine of theta plus sine of theta. So derivative of the first term times the second plus derivative of the second term times the first term, which is e to the theta sine of theta. And all that is divided by dx d theta. So dx d theta is defined here. So the first derivative of f of theta times the second term plus derivative of the second term times the first term. And we want to find dy dx when theta equals 0. So when theta equals 0, we just go ahead and plug in 0 for all of these expressions, plus cosine of 0, e to the 0, sine of 0. So before we move on into plugging in 0 for the denominator, to save a little bit of time on the actual exam, we can take a look at what values create 0. So sine of 0 is actually 0, which makes this whole expression 0, and which makes this whole expression 0. So right now we have 0 plus 0. So no matter what the denominator is, we know that 0 plus 0 equals 0 over something, which means that our dy dx equals 0. So polar differentiation isn't very complicated compared to the parametric differentiation. We're simply converting it into the parametric form and applying the same exact principles. So we can see this as an extension of the parametric differentiation methods. So thanks for watching Educator.com. We will see you in the next lesson.